Good day, everybody. This is Chris with the Ancient Scholar, and this is actually a video that'll be covering an assignment that I'm working on. This is an assignment for a class I'm taking for the Laboratory Quality Improvement Quality Assurance, summer of 2014. All right, this is involving an assignment that revolves around the concept of validating a analytical test. The analytical test that I'm going to be talking about today is the arterial blood gas, or the ABG, specifically the arterial blood gas. And specifically, I'm going to be talking about an analytical value known as the PaO2. That's the partial pressure of oxygen. All right. So what we have in a clinical lab situation, okay, is a machine, and you guys are familiar with these because you work with them, and there's a little display here that you can work with, and there's a little port here. Okay, you've got your little ABG machine here. So what do? Well, you draw a sample. All right, so here's my little syringe. All right, there's my syringe. It's got some heparin in there. And you draw an arterial sample of blood from your patient. All right, you take that sample. All right, you place the sample into the machine. Some magic happens in that machine. Okay, some magical, mystical stuff happens. And out pops your ABG report. On that ABG, it gives you the pH, the PaO2, the PaCO2, the HCO3, the bicarb. It may give you some electrolytes as well, like sodium and potassium and chloride. And if you do co-oximetry, it may be able to give you, the met hemoglobin, carboxyhemoglobin, etc., etc., etc. Okay, so what I'm going to do is I'm going to try to talk a little bit about this magic that goes on, and specifically what we're going to be talking about is the PaO2, measuring the partial pressure of oxygen in this sample of blood. That is the specific analytical technique that we're going to be doing, and of course this is very important in clinical medicine. It's very helpful for looking at how well a patient may be oxygenating. So I think where I want to start, even though this is lab QA, QI, I'm talking about validation, what I want to do is just explain a little bit about how the ABG machine actually works. And then in the paper that I'm turning in, of course there will be a full description of how I would go about validating an arterial blood gas machine. So these videos are more about how does a darn thing work? What are the physical principles? Okay, so really what's going on is we're performing something called hemoximetry. And so I'll just throw that word up there. All right, hemoximetry. And you guys are all familiar with this, or most people are familiar with this, because there are machines called pulse oximeters. And we know that this has something to do with light. And so the principle that underlies hemoximetry in pulse oximeters and arterial blood gas machines and so on, that the principle is known as spectrophotometry. So let me go ahead and put that up there. Spectrophotometry. What a word is that? Okay, so spectro has something to do with spectrum, and photometry has something to do with photons, with light. So it's something to do with the light spectrum, okay? And the principle of spectrophotometry really comes from our understanding of the atoms and molecules. And our understanding goes pretty much as follows. We'll just kind of use the good old Bohr model of the atom. You have your positively charged proton, and then in very discrete energy levels, okay, around the nucleus of the atom, you have electrons, which are negatively charged, and they're attracted to the protons through the Coulombic force. And we actually know that they exist in kind of a cloud of probability density, but I'll just kind of draw that as an orbit to kind of simplify the model for the high yield understanding. And we know that those electrons in their orbits, quote unquote, are in very specific levels of energy. So if I have this atom here, this electron, maybe it has negative 10 units, negative 10, or maybe we'll do negative 13.7 eV. All right, that's actually the ground state of the hydrogen atom, okay? And then we know that the energy levels are quantized. So if this electron wants to go up to a higher level of energy, it can't just take any level. It's bound to a very specific level. So if this is my ground state, my first level, this is my second level, and maybe the second level, I don't know, I forget what the N equals 2 is for a hydrogen atom, so I'm just going to make something up. It's a kind of a big jump, so maybe it's like negative 8 eV, okay? The value doesn't really matter all that much, but what matters is that it cannot take any value in between negative 13 and negative 8. It can only be at negative 13, negative 8, or whatever the next higher level of energy is. It can't have any energy levels in between here. So to get that electron to go up to that next level of energy, that electron has to be given the exact amount of energy that separates these two energy levels here, okay? In this case, it would be what, about negative 5 or 5.7 electron volts. Okay, so we know that when we talk about the energy of light, okay, the energy of light is related to the wavelength. All right, it's related to the wavelength of light, and we know that smaller wavelengths equal higher energies, and larger wavelengths equal lower energies. So it's possible that if I found the exact wavelength of light that corresponded to this difference in energy here, what I could do is I could shoot a photon of light, okay, at this atom here, and if it was exactly the right energy, just the right difference, okay, between those energy levels, I could give that electron enough energy to go from n equals 1 up to n equals 2, right? It could have, and then what would happen was it would absorb this light, okay? So I could shoot light at an atom or a group of atoms, and if it was exactly the right wavelength, the atoms would absorb that light, and I would not see, if I was kind of looking here with my little eye, I would see the light would get absorbed, and I wouldn't see any light come out on the other end if it was 100% efficient. That is how this concept of spectrophotometry works. That's fundamentally how it works. Is we know that electrons and atoms and molecules will absorb very specific wavelengths of light. So when it comes to oxygenated hemoglobin, okay, in the blood, okay, so I have oxyhemoglobin. I have oxyhemoglobin. Oxyhemoglobin is going to absorb very specific wavelengths of light, okay? So to kind of illustrate this, let's say that I have 2 samples of blood, all right, and the container holding the sample, the thickness of the glass or plastic in the container, and the amount of blood is exactly the same, okay? We have to make sure that that's all the same, okay? It's the same width, the same amount of blood, okay? But within that blood, let's say that this one up top only has a little bit of oxyhemoglobin, and this one down here has significantly more oxyhemoglobin going on, okay? And when we talk about labs, you're probably used to, when you talk about this, you're used to the terms solvent, and solute. And we say that solutes are things dissolved in solvents. So in this case, the solvent might be the blood, and the solute might be the oxyhemoglobin. That's not totally 100% accurate, but that could work as a good approximation. Well, when it comes to labs, there are some other terms that I just want to throw out there. You have what's called your media, and your media is kind of like your solvent. So you have your media or your matrix. Okay, some people will say matrix, and that's just that's what your thing of interest is dissolved in or is suspended in. So you're not necessarily interested in all the other stuff in the blood. We're interested in the oxyhemoglobin because that's what we're trying to analyze. So the thing of interest, the kind of the solute, if you will, is what we call the analyte in lab quote-unquote terminology. All right. Now, in some cases, in some labs, we actually have to extract the analyte from the matrix, and there's a whole process involved in there. When it comes to hemoximetry, like a pulse oximeter, an arterial blood gas machine, that's not really the case. We don't have to extract it, but sometimes you do. In a lot of cases, you do actually. This just happens to be one of the cases where you don't. Okay, so here we go. So let's assume that we have found a wavelength of light, okay? We have found a wavelength of light that is pretty well absorbed by oxyhemoglobin. What I can do is I can have a source. I can have a source of light, and we're going to say it's the same wavelength, and it's the same intensity, okay? It's the same wavelength, it's the same intensity up here as it is down here. The thickness of the glass or plastic walls and the level of the blood, all that's the same, and the only thing that's different, so we have to control for everything else, but the only difference is this sample has a little less, has less oxyhemoglobin, this sample has more. So as I shine light through here, okay, and the thickness of this arrow is the intensity. So I shine light through here, some of that is going to get absorbed by this oxyhemoglobin. So when I look at it, okay, so here is my little eyeball here. I'm not really looking at it, I'm actually having a machine look at it, but the intensity will have gone down a little bit here because there was some absorption that occurred. However, if I go down here and I shine light, the same intensity, same wavelength, there's more oxyhemoglobin here, so more of that will get absorbed, and the intensity is going to be much lower down here. Okay? So that really is the fundamental concept. This is spectrophotometry right here. All right? So let me just define a couple of terms now so we're good to go. So there are some terms that come out of spectrophotometry, and the first term is something known as transmittance. So let me put that up. Transmittance. And transmittance is actually a ratio. In transmittance, if I have my sample here, okay, I have light coming in, and then light coming out, and the width of the arrow is the intensity, okay? So this is intensity 1 here, and this is intensity 2 here. Transmittance is just a ratio of the intensity going in, okay, so that would be I1. It's a ratio of I1 divided by the intensity coming out, or I2, we'll say. All right, that's just a ratio of I1 to I2. So basically, what does that say? That says that the lower the transmittance, okay, the lower this ratio is, the more opaque, okay, the more opaque this sample is to the specific wavelength of light that I'm using. And the higher the transmittance, okay, a greater transmittance as it approaches 1, is going to give me a less opaque. All right. Okay, so there is less of the analyte in there. All right, the next concept is something known as absorbance. And absorbance is, in a certain sense, the opposite of transmittance. Transmittance is how much actually got transmitted through there, how much actually made it through. It's a ratio of what was going in to what made it through. Absorbance is how much actually got absorbed here, or it's a way of looking at that. And really what absorbance is it's just the negative log, that's taken to the base 10. It's a negative log of the transmittance. Okay, so it's the negative log base 10 of I1 over I2. Okay, so what does that value tell us? Well, it tells us that a low absorbance, okay, is going to be more absorbed. All right, more absorbed. A higher absorbance is going to be less absorbed. All right, cool. All right, so now we know what transmittance absorbance means. Now what we'll do is the fundamental physical principles, aside from the quantum mechanics, the pseudo quasi-quantum mechanical model that I showed you earlier, is what's known as the Beer-Lambert law. The Beer-Lambert law. Okay? And the Beer-Lambert law says that the absorbance approximates the length of the pathway of the light. How long is that pathway? And that's multiplied by the concentration of the stuff that is absorbing the light. In this case, it would be the analyte. And just as an aside, a concentration is almost always going to be molar. And in chemistry, it's common to put brackets around that to tell you that it's molar. It's a molar concentration. That's how we measure it. Specifically, the law goes as follows. Absorptions equal some constant I'll call K. I believe that epsilon is used for that constant in some cases. I'm just going to call it K for constant. Or you could call it C for constant, but we C is concentration. So we'll go all German on you guys here. So some constant times the length of the pathway times the concentration molar. All right, so that's the formula. Okay, so what in the heck does that mean? I've just been blabbing on and on and on. What does that mean? Well, let me show you here. What that means is I can graph this here, right? Bam. All right. So let's say that I have I'm looking at a concentration of some analyte. And this is 0.1 molar, 0.2 molar, 0.3, 0.4, ... All right? And this over here, we will make this over here the absorbance. All right? And then what I want to do is I just kind of want to graph this guy out here. So let's say that at a certain concentration, I know the concentration, and I shine some light through, I get 0.5 here. All right, so put a dot there. Bam. All right, and then I go, you know what? 0.5, 1, 1.5, 2, etc., etc. And then I go, hey, you know what? Let's see what 0.2 will give me. All right, so I'll go to 0.2, and then I get 1 there. All right. Now the cool thing is, I can connect these dots, right? And these dots make a line. Hey, cool. All right. How about that? Well, let's go back to this. So what does that tell me? Well, with a linear relationship like that, that tells me that I can explain, the equation for this line can be written as y equals mx plus b. And if we look at the Beer-Lambert law, A equals K times L C molar, K might be epsilon. What does that tell me? Well, this guy right here, this constant, okay, this constant is m. And m is the slope of the line. And that's really handy because now what I can do is I can put an unknown sample in, right? I can put an unknown sample in. I don't know the concentration. I can just put it in. I can measure, and let's say that I get 2 here. All right, so this is the A that I get. Well, what I can do is I can plug that 2 into this equation, and I know m. And because I have a straight line here, and this is a linear relationship, all I have to do is just kind of plug 2 in here, bam, like that. All right, and I'll extend this little line out. 1.5, 2, 3, and obviously this is not to scale, but this should be right around 4 there, but hopefully you get the point. This lies on a line. I can use my slope equation, and I can figure the concentration out based just on the how much is absorbed based on this Beer-Lambert law, based on the spectrophotometry, and that is fundamentally how an arterial blood gas machine calculates the PaO2 in blood. Is you shine light through your sample, and depending on how much of that light at a very specific wavelength, mind you, gets absorbed, you can calculate the concentration using fairly straightforward mathematical principles. Okay guys, I'm going to go ahead and cut the video off here, and then on the next video I'm going to kind of just show you, I'm going to kind of draw out, very simplified, the guts of an arterial blood gas machine and show you what's going on there. All right, as always, thanks for hanging in there.